Hi, welcome to the presentation of case study prepared by Jackie Bell, David Rivers, Francia F. Riesco, and myself, Dmitry Gavrilkov, as the part of Data Engineering for Analytics course in Harvard Extension School. And today we will be talking about data engineering in Netflix. Netflix is pioneer in the delivery of streaming entertainment, launching their services in 2007. The company provided services to approximately 222 million paid memberships in over 190 countries. At Netflix, data and machine learning pipelines are widely used and have become central for the business, representing diverse use cases that go beyond recommendations, predictions, and data transformation. A large number of batch workflows run daily to serve various business needs. These include ETL pipelines, ML model training workflows, batch jobs, and many others. Netflix utilized a combination of proprietary and third-party technologies to operate the business. This includes the technologies that the organization had developed to recommend and merchandise content to consumers, as well as enable fast and efficient delivery of content to members in their various consumer electronic devices. The company relies heavily on Amazon Web Services for providing distributed computing infrastructure platform for business operations. Netflix is a big data-driven organization, and many products and business decisions are totally based on data analysis. Netflix revenue comes from a monthly subscription service, so the goal for the company is to keep users subscribed and to get new subscribers. But offering new content is not everything. What is also very important is to keep people watching content that already exists. To be able to recommend content, Netflix is collecting data from users, and collecting a lot. It is known that in 2016, Netflix analyzes about 500 billion user events per day. That results in a stunning 1.3 petabytes every day. All this data allows Netflix to build recommender systems for members. The recommenders are showing content that people might like, based on viewing habits or what is currently trending. According to a privacy policy, Netflix collects data including device identifiers, geolocation, browser time, and details subscriber gave it to sign up, such as email address and payment information. If you're using Netflix on your browser, cookies and web browser history can be used to collect information about your interests. This slide shows one of the first productionized pipeline in Netflix. There are several hundred event streams flowing through it. The sole purpose of the original data pipeline was to aggregate and upload events into Hadoop for batch processing. As you can see, the architecture is rather simple. Chakra collects events and writes them into S3 in Hadoop sequence file format. Then the big data platform team further processes those S3 files and writes to Hive in Parquet format. End-to-end latency for the entire pipeline is up to 10 minutes. That is sufficient for batch jobs, which is usually scanned data at daily or an hourly frequency. The centerpiece of 1.0 pipeline is Apache Chakra, which is an open source data collection system for monitoring large distributed systems and which is built on top of Hadoop distributed file system. As a data platform for generating insights, the Chakra pipeline was a good start. At that stage, it was very important to be able to create hourly and daily aggregated views of user behavior. The only problem was, with batch processing, you're basically looking into the past. For Netflix and data-driven companies in general, looking into the past is not enough. They want a live view of what is happening. Also, Chakra lacks some features of the modern processing platforms, such as, for example, data replication that makes pipeline fault tolerant. With the emergence of Kafka and Elasticsearch over the years, there has been a growing demand inside of the company for real-time analytics. And by real-time, we mean sub-minute latency, which led to further evolution of a pipeline's architecture in Netflix.
Netflix's business model canvas is based on acquiring and producing content and distributing it via its platform. What makes it so appealing is that it offers on-demand content viewing and personalization. List of Netflix partners: Amazon AWS. The whole Netflix technology platform is hosted on Amazon AWS. Media producers who then license content to Netflix. Filmmaker guilds, directors, actors, writers, and their guilds, unions, and the film industry. Cinemas and theaters, TV networks, consumer electronic producers, regulators. List of Netflix cost structure: research and development, content purchases, content production, infrastructure, marketing, payment, general, admin, employees and staff. List of main Netflix revenue sources: subscription model, the main source of revenue for Netflix. Product placement, marginal earnings not significant. DVD rental, licensing, own content, ads. List of main Netflix resources: brand, apps, website, platform, content library, Netflix studios. List of main Netflix value: on demand, streaming, binge watch, original content, among other features. Netflix future challenges. Cash flow challenges. Netflix said cash burn peaked last year, and it expects to achieve a free cash flow positive in the future. A positive cash flow would not come from scaling back spending on content, but rather from revenue and operating income increases such as ads, services, and licensing own content. Competition challenges. Netflix has been streaming movies and TV shows for 12 years. With more competition in the market, customer acquisition costs for established markets are higher. Moreover, with more competition, it will be a higher churn rate as customers are tempted away from the platform. International expansion challenges. International customers are more significant than the USA and Canadian markets. Therefore, future challenges to Netflix are incrementing subscribers' growth and improving retention in bigger markets such as India and Brazil. Customer retention challenges. This is the most critical challenge. Netflix needs to identify the best options to improve customer experience and retention to make its business increase and keep bringing new features and series.
It was clear that Netflix needed real-time data.
Netflix future challenge.
It was clear that Netflix needed real-time data. It was clear that they needed real-time processing technologies, needed stream processing in order to be truly competitive and to secure their market position. So let's talk about how they began to move away from their previous version 1 data pipeline towards something new. This slide shows essentially their version 1.5 as they took a baby step towards a new Kafka architecture. They essentially bolted a mini Kafka pipeline onto the existing Chukwa system to start to experiment with and create the beginnings of a real-time pipeline. In this version, about 30 to 35% of events were branched and routed to sinks like Elasticsearch or a secondary Kafka. And this ended up being a good proof of concept for Netflix and proof that a Kafka architecture could work for them. But maintaining this was a very complex process, and maintaining the router as a managed service proved just too challenging. And it was clear that all this needed to be streamlined and the old system needed to be completely re-envisioned. The solution was what Netflix calls the Keystone Pipeline. It's a unified event publishing, collection, and routing infrastructure for both batch and stream processing. The old Chukwa system, as you can see, was entirely removed and replaced with a Kafka architecture designed to deliver a robust support structure for real-time analytics. There are 3 parts to it: data ingestion, so they can use their Java library and write directly to Kafka, or send to an HTTP proxy, which then writes to Kafka. There's data buffering. Kafka serves as the replicated persistent message queue. And there's data routing, moving data from fronting Kafka to various sinks, like S3, Elasticsearch, or a secondary consumer Kafka. You'll notice 2 sets of Kafka clusters in the Keystone Pipeline: fronting Kafka and consumer Kafka. Fronting Kafka clusters are responsible for getting the messages from the producers. Consumer Kafka contains a subset of topics for real-time consumers. Netflix says when it comes to this data architecture, stability is really prioritized for the fronting Kafka clusters. This is their gateway for messages. Client applications are not allowed to directly consume data from these fronting clusters to make sure they have a highly predictable load. Let's look under the hood of the Keystone pipeline. Let's look under the hood of the Keystone pipeline for a moment. Netflix has carefully tested strategies for deploying Kafka clusters. Multiple small Kafka clusters are favored as opposed to one giant cluster to cut down on operational complexity. There's a limit on the number of partitions in each cluster to improve availability and cut down on latency for requests. The ultimate goal is really stability. They are always working towards an even distribution of replicas for each topic to make it easier to detect outliers and plan for capacity needs. And they use a dedicated Zookeeper cluster for each Kafka cluster in case of Zookeeper issues. Netflix really seems to have a strong culture of chaos engineering, so planning for failure. They plan for the worst and hope for the best, and that ethos is evident in design choices Netflix has made with the Keystone pipeline. Producer and consumer traffic can be moved to a new Kafka cluster if the primary is in trouble. For each fronting Kafka cluster, there is a cold standby cluster. The failover cluster is designed to be free from replication issues the original cluster may have, and Netflix says that failover can be completed in less than 5 minutes. Netflix also has extensive dashboards to monitor traffic flow down to topic level and keep their eyes on their dedicated monitoring service. The monitoring service tracks things like broker status, especially to detect if it is offline, and to track the broker's ability to receive messages and deliver messages to the consumer layer. The monitor also measures the latency of these messages. It can also track partition count for the consumer group and make sure that each partition is being consumed. And it monitors checkpointed offsets and compares them with broker's log offsets, making sure nothing is stuck and making sure there are no big lags. Keystone by all accounts. Keystone by all accounts is really delivered for Netflix. However, there's always a question of what's next, and there's always a need for evolving architecture solutions for emerging use cases. So Netflix has apparently decided to work on data mesh as the next-gen data pipeline solution. Here's a very brief look at where Netflix architecture is headed next. Data mesh is a fully managed streaming data pipeline product. It's split into a control plane and a data plane. The control plane, the brains of the operation, as you can see here, receives user requests and orchestrates pipelines. Once it is activated, the pipeline does the actual data processing work. A data mesh pipeline reads data from various sources, applies transformations, and eventually syncs the event data into the destination data store. Kafka is used as the transportation layer. A source connector is a data mesh managed producer. It is able to talk to the data mesh controller to automatically create and update sources. A processor is a Flink job. It reads events from upstream and applies some business logic to each of them. An intermediate processor writes data to another transport, and a sync processor writes data to an external system like Elasticsearch or a separate Kafka topic. Data mesh does enforce schema on all the pipelines. All the events passing through the pipelines must conform to a predefined template. Netflix says schema is prioritized in order to have better data quality and more data discovery opportunities. Data mesh is still in the early stages for Netflix, but all of these data architectures and systems are ways that Netflix has tried to evolve its infrastructure to achieve the ultimate goal, which is to provide a unified system for both batch and stream processing to deliver data that can be relied on to make decisions.
How does Netflix take advantage of this big data stuff? To answer this, I'll need to point out what type of data is being stored and know the purpose of the storing the data. Finally, I'll touch on their data analysis approaches. Earlier we talked about how the data is stored, but items that are stored heavily depend on how the user is connected to Netflix. If a user is connected using a web browser, scrolling, clicking, and even browser cookies are collected. However, if a user is like myself, using an application on a device like the Xbox, then the data collected will be different. Some of the essential data elements are movie genre types, time of the day the user is watching videos, and the duration they are using Netflix. These historical data elements can be used to identify if a user is falling asleep. With a combination of collected data elements, Netflix is able to identify user habits and predictions. Netflix can take advantage of these forecasts to then make planning for new productions. Additionally, they can use the collected data for security purposes too. They have the user's habits and their login locations that can help identify fraudulent usage. Some of their analytical approaches use statistics or machine learning to identify new markets within the video streaming industry. Even a simple distance form for a recommendation system can be very useful to identify what users want to watch. How does Netflix? As mentioned, we can make user recommendations using a simple distance formula. In this approach, instead of going directly to predict a video to recommend to a user out of the millions of options available, this technique attempts to find the most similar user to whom Netflix is going to recommend videos to. This example is using the Euclidean distance to find the most similar users, and there are hundreds of other distance formulas that can be used. In general, the shorter the distance between two users, the more similar in taste in videos they have. After the most similar users are found, then Netflix will recommend the video content that the other hasn't seen. In this example, in the table we are using video ratings between Netflix customers. But what if there are a lot of similar users and Netflix can't narrow it down to just a few users? The data scientists can then add additional features like adding time as a factor, not just who saw the same movies, but which of them watched them around the same time. With this model approach, Netflix can add an infinite amount of dimensions using the same formula. As continuing with the same scenario, here is the computation if we were going to make a video recommendation to the user Veronica. First, we start off by calculating the distance between Veronica and all the other users. Here you can see that the bold lettering is the distance outcome between the two users. The smallest distance between Veronica and the other users is Haley. The next step is to identify the videos that Haley has seen but Veronica hasn't, which are Stranger Things, Bridgerton, and The Umbrella Academy. However, Haley didn't rate the other two shows too highly, so Netflix would recommend just the Stranger Things. This wraps up utilizing the Euclidean distance for a recommendation system. Just want to say thank you for watching and listening to our presentation. Thank you.